What's up, my boys? So, I'm, last video was, a doozy. So, calm now, and, let's get into determinants. I'm sorry, I was, practicing a line. I was gonna do a skit for this video using that, acting, but... So, we're going to do determinants. So, yeah, I need you to kind of think of two concepts, right? And also, I think a great video for determinants is 3 Blue, 1 Brown. I may or may not need the book determining if we get into permutations this week, because nobody really... I don't remember the permutation thing, the little determinant long thing. So, let's get into determinants. First of all, how do we define an n by n matrix? Well, it's just so usually mathematicians identify it as a vector of vectors, right? So there's n components in this vector, and it contains vectors alpha through alpha n, and alpha 1 can be represented as an m-length vector, right? b1 all the way to bn, right? So that's kind of what a matrix is. It's just a bunch of vectors in a vector, right? We say this is a bunch of vectors. It's kind of like holding data, again, like people say. So if you have 1, 2, 3, 4, 5, 6. Let me see if this is recording actually. Yeah. So and also I improved my video quality because the front facing camera sucks, so I fixed that stuff. So yeah, that's what a matrix usually is. It's just a bunch of vectors in it. So if we have, for example, B matrix 1, 0, 0, 1, this is the vector 0, 1, 1, 0, and this can be represented, this matrix can be saw as, right, this and this, and you might notice that it's I hat and j hat, the basis vectors for R2. So that's what we think of a matrix. I also want to get into the definition of a matrix by linear transformation, right? So you could also think of a vector, right, as a linear transformation. If you don't know what a linear transformation is, watch my videos on tensors. So it's a linear transformation and of vector spaces. And in this case, in most cases, right, we just look at the matrix of real numbers, right? So each entry is a real number, right? So we're going to look at the n by n matrix, right? So this would be Rm to Rn, right? And this is a linear transformation. So that means for, since this is Rm, this is going to have m inputs, n outputs, n inputs to a vector with n entries, right? So we can think of alpha 1 or alpha 1 all the way to alpha m, right? And if we have that for m plus beta, no, this is too complicated. So you could think of it as a linear transformation of two spaces. So the m by n matrix is transforming m vectors, right, into an n space, right? So that's also what we could think of it, and that's what kind of 3 Blue, 1 Brown gets into. So we could think of the matrix as intuitionally n vectors and stuff, or we could also think of it as this, right? And hold that thought, okay? So now we're going to get into a determinant, right? So how do we define a determinant? Why do we care about a determinant in the first place? If we want to define a determinant, we first have to understand why do we care about it. So, or go on along the way. But you are familiar with the determinants already. So what is it really? So it's the area between two vectors, right? So the determinant, so how do we find the area between two vectors, right? So this is how. So first of all, we're going to define the determinant function. All right, we'll call this determinant function as a mapping between this to R, right? This is the space of all n by n matrices, okay? That's what this denotes. So this is the set of all n by n matrices. That's all it denotes. Okay? So it goes from an n by n matrix to some real number, right? So if you want to actually calculate it, right, we could find the determinant of A, and A is an element of Rn times n, and this is going to be equal to some real number, right? We'll call it C, which is an element of R. So that's what this is saying, right? So what are the properties of this function, right? What are the properties? So let's find the properties. Well, first of all, we're going to have the property that the determinant of I is equal to 1. What is I? It's the identity matrix. What is the identity matrix? It's the n by n matrix with where the diagonal of this matrix is 1 and every other entry is 0. Right, so that's what it is. So this is the identity matrix. This is an identity matrix. And we can continue so on, right? So why this matters is that if you notice that if you multiply this matrix by any other matrix, it's going to be the same. So you could kind of think of it as the 1 for matrices, right? So you notice how 1 times any real number is going to be that real number, right? So that's what the identity matrix does. So why does this make sense, right? First of all, let's look at the identity matrix for R2, right? Which is this I hat and J hat, right? So let's look at this space, right? We have I hat, we call this I hat, and we have J hat, right? So this length is 1, and this length is 1, and the area is going to be the area of a square with one side, right? So 1 times 1 is 1 units cubed, squared. So that makes sense, right? So the area between that is just going to be 1, right? 3 Blue 1 Brown also has a great video of it if you want to know the other way we look at determinants. So second property states that if 2 rows are the same of, we'll call it matrix A, the determinant of A is equal to 0. Why does this make sense? Well, first of all, let's look at R2, right? If 2 rows are the same, we're going to have A, B, B. So, already, we're taking the determinant of this. Notice this. Notice how they have the same exact components, right? So AA, BB. BB8. So what thing does this generate, right? So first of all, let's look at AA. So we have A, and we have B, so first of all, we know that they overlap, right? Now, why does that make sense? Well, these are actually the, I believe, no, yeah, so, yes! No, I scratched my, ay, cochino, puta Okay. So, okay. Holy shit. Okay, so, oh my god. Okay, it's fine. It's all better. Oh, cochino. So, fuck. So, okay, so here's why they'll overlap all the time, right? Why do they overlap? Well, we notice how we define vectors. We define vectors by their length and their direction. Where they go. Where do they go? So, how do we talk about direction without angles, right? That's also how we define a vector. So, the angle there from the origin is going to be... Okay, so notice, okay, how this is the x component and this is the y component, right? And we notice that the tangent of theta of an angle, right, of a triangle, right, is going to be equal to the opposite side over the adjacent side, right? And we'll say the adjacent side is x and the opposite side is y. Oh my god. So, notice how tangent of theta of the tangent of the angle the vector makes is going to be y over x, right? And the tangent of theta, yeah, we'll call this x2 and y2. So tangent of theta is going to be y2 over x2. But guess what? X is equal to y, and y2 and x2 is 1. So this is equal to 1, this is equal to 1. So they're going in the same direction. So they're going to overlap. So these are unit vectors, basically. So, God, these are going to be unit vectors, right? So, since they're unit vectors, right, what's the area? So, and guess what? They're going the same direction, right? Or not unit vectors, but they're going to be, they're basically just going to be 1, 1, right? Multiplied by A and multiplied by B, right? Not unit vectors per se, but they go the same direction. That's why they go the same direction. So guess what? If two vectors are going the same direction, what's the area between them? Well, what is between them? There's nothing between them because they're going the same way. So there's no area to calculate between them. But you may be saying, guess what? Wait. Hold up. What about, okay, so this works in 2 dimensions, right? But what about the 3rd dimension? Well, so, or any other dimension. God. Okay. So, let's see how long this is. So, the case for the 3rd dimension is right. And you only said 2 rows have to be the same, right? So let's just make another matrix, right? So A, B, B, C, C. Now we add another vector, right, from this. And now, maybe they don't have to overlap, right? But, so we'll call this D, E, F, right? Say they're different, right? Well, now this is how I like to think about it, right? So, we have these pens, right? They'll represent these 3 vectors. A, B, C. Right? So, originally, we had 2 vectors being the same, right? They're going the same direction, right? So, think of them just kind of overlapping, right? So now we want to add C. And they're overlapping, but wait. So now we want to extend it. And now they're going at... this one will be this way up, right? We'll represent this entire area as 2 dimensions, right? And we'll represent this area as the third dimension, right? So, oh, wait, okay, this one's up a little bit, okay? And we also want this one to be up a little bit. But they still have to kind of follow some component rules. So they're going to be fixed at this kind of thing, right? They may differ from length, right? But in actuality, they're always going to be like this, right? So, but the problem is that, well, they don't really differ from two dimensions then. If they're always going to be like the same direction, and we want to find, now, this is the volume between them, there's no volume to calculate, and we could think of the areas between them as still 0. So 0 times the other vector is going to be 0, right? And second of all, how do we find, we can't find the determinant by an m by n matrix if m is not equal to n, right? And that's what we're basically doing here. Because now, this is basically finding the area between 3 vectors in 2 dimensions, right? So you could think of it as this, right? We're basically finding the area between 3 vectors in 2 dimensions. Or whatever. So we can't do that. And they're overlapping. So what's the area between them? So how do we even find the volume between them? It's impossible. They're still overlapping and they're still going in the same direction. And since we can't define oh, and since we can't define that, it's impossible. So hence that rule. Right. So final one. Again, I want you to again look at this. So they're going the same direction, right? They're basically same vector, maybe a little different in how far they go, but they're going the same direction in all, right? So now you want to add an extra layer of dimensionality, right? So now this one goes up a bit, this one also goes up a bit, and this one also goes up a bit. But no matter where you go, they're always going to have to be like in this kind of formation, right? They're always going to be like this. Maybe this one's slightly below, this maybe slightly above, and this one's slightly like this. But they're always going to have to be kind of like this. So you can't find a volume between these, and you can't find anything between these, really. So that's the issue with it, because you're basically now trying to find the area between 3 vectors, and that's not what you could do in a determinant, right? And it gets even nicer with 3 Blue 1 Brown's video on how. So 3 Blue 1 Brown video, it says determinants kind of tell you the change of basis, right? So we call this basically the basis matrix, kind of, because we have I hat and j hat, right, as the basis vectors for R2, right? So, man, I'm feeling shit. So, the determinant tells us the direction and area of how the basis change, right? And that makes even more sense, because if you try to find the determinant of a 2x3 matrix, that's impossible, because you can't generate R by 3. You can't have 3 different vectors to kind of serve as a basis for R. That's ridiculous. So hence that would be 0. So the final one, or the third one, right, before we kind of get into the third property that we kind of have to explain, is that the determinant, if the determinant of A equals, so if A prime is a matrix by switching two rows of A, the determinant of A prime is equal to the negative determinant of A, right? So we're switching two rows, right? So let's look at the base case, the identity matrix, right? If we switch the two rows, we get 0, 1, 1, 0, right? So what does this do? Notice how we have 4 quadrants, right? And notice how we kind of always define this one to be negative x. I'm going to get a new marker. So negative x, or negative y, and negative x, right? So if we're doing this, right, we call this I hat and j hat, right? What this matrix is doing, I hat, j hat. Is, come on, it's completely rotating the I hat and j hat's position. So now we have I hat and j hat. Well, why can't we just do that and still have the area between them being 1, right? Well, we can't have the area between them being 1 because we're also changing the basis, right? So how do we define, for example, the determinant between this and this, right? How do we define the determinant between these ones? And this is in the negative quadrant. So how do we have negative area without having this property? Well, we can interpret this as j hat being, I believe, no. How do we find the area between this and this? So this is the negative quadrant. So we kind of think of everything below this area. So this will be positive area, and this will be negative area, right? So now we're switching these two, and we're kind of changing the basis, right? So now these bases are changed, and we're kind of finding the area between this and this. So, we'll definitely need 3 blue, 1 brown for information. Actually, that would use the linear property. So I want to get into the final property. So now, if we have, right, it's the determinant function is n linear, right? So if we want to represent each row of a matrix as alpha of I, we'll call this each row of the matrix determinant of alpha I, alpha n, right? And we want to scale one of the rows, right, by a number, and we want to add another vector by it. B is in R of n, and C is in R, right? Then we can ignore all of these for a second, right? Fix them, quote unquote, and we could say that this is the determinant. This is equal to C times the determinant of the original output plus the determinant of B replaced with A of I all the way to A of n. Right? So this is actually how we calculate it, right? So this is actually how we calculate determinants and find the area by its linearity. And it also works because it preserves linearity, right? So notice how when we say vector space, V is a subspace of W, right? Or actually, it's better to say W is a subspace of V, right? We say that if alpha is in W, beta is in W, and some scalar over the field, so W is a vector, V is a vector space over a field, right? Then W is a subspace of V, if we scale the vector, right, A, and we add B, if this holds, W is a vector space, right? So this is basically saying it's closed under addition and scalar multiplication. So that's how we define, that's how we know if W is a subspace of V, right? So this kind of applies to this, right? So it's kind of preserving its linearity of a vector space. It's kind of preserving the vector space properties, right? So that's why we have that. And I'll get to this one more after I finish this. So, and if, for example, right? For example, we have this matrix, 2, 2, 0, 0. We'll go with this simple example, right? Two, 2. What's the area between 2 and 2? This is 4, right? So this is equal, so the determinant of this is equal to 2 times the determinant of 1, 0, 0, 2, which is equal to 4 times the determinant of 1, 0, 0, 1, which is equal to 4 times 1, which is equal to 4. So that's why that makes sense. And then, of course, if we change it and stuff, this helps us find the area between vectors that are a little wonky and hard to find, like this, and this, and this, right? And this and that, right? So that's how we find that determinant. Right? So the final property, I guess, I kind of never really explained well, was the determinant of A prime, which is equal to negative determinant of A. The reasoning for this is the change of basis, right? So we notice if we switch this and this, right? We switch it and transform it to 0, 1, 1, 0, right? We're kind of rotating the basis, right? And how we kind of define rotation, right, on a grid, right? On the grid, right, is if we want to find the area between anything from this quadrant, this is y, negative x, negative y, and x, right? All of this will be negative, right? So this entire area is going to be negative, and this is going to be the positive area. So we can kind of think of it as, oh, we're rotating this 100 degrees, so that's going to how we're going to define negative. So this is rotating the basis vectors about 270 degrees, I believe. It's changing it by rotation. So if we're changing the area by rotation, it's going to be a negative area, right? So those are the properties of the determinant, and I will get into permutations for the next video. Thank you. And if you want more information of determinants, again, I really recommend 3 Blue 1 Brown, or learn this shit on your own. Goodbye.